Good afternoon. This is mini lecture B on bonding of atoms and how the periodic table encodes bonding and other properties of the chemical elements. Let's take a look at it. Um, Here's the periodic table, and one of the things that scientists discovered starting with Mendeleev is that the chemical properties tend to occur in columns. In other words, if you arrange by atomic number, uh, the elements in each column have very similar properties. Now, one of the easiest ones to identify is the column on the far right. That's the noble gases, group 8A. And the noble gases over there in the right column, they tend not to combine with other elements, and they don't really form with other noble gases either. They tend to be monatomic gases or substances. And that has uses. I mean, for instance, argon is used to fill spaces where you're manufacturing something that you cannot afford to oxidize anything. And a famous example of that is uranium. Uranium metal, pure uranium metal, uranium 235, when you put it in a lathe or any kind of a milling machine where they shave off the metal to make it, rectangular or round or something like that. Those little shavings they'll burst into flames. They'll start to oxidize in oxygen, right? And that's something they found out during World War II in the Manhattan Project. It was kind of dicey, anyways. So what you would want to do is use argon or one of the other noble gases to fill your chamber and avoid getting oxidation. Another really important property uh, in the chemical elements is what we would call oxidation. And that means to lose an electron or maybe one or two electrons. The alkali metals in the leftmost column, uh, those are the ones that are the most easily oxidized. And the next few columns after that, the second column and so forth, are pretty easy to oxidize too. And that is important because of bonding. The, the theory that we currently follow, that we think makes sense, is basically that the outermost electrons in the outermost orbital levels are responsible for bonding and chemical reactions. Okay, they're not as tightly bound. They're at these outer orbits. So if you think of, if you were to think of it as like a gravitational system, the higher your satellite is in orbit, the easier it is to launch it off to Mars. You know, whereas if it's in a low down orbit, like about 200 miles where the space shuttle and the space station are, you need big rockets in order to escape the gravitational pull of Earth and head out to Mars. But if you're way out there, like where the communication satellites, the geosynchronous satellites are, easy or easier. You still need a pretty good rocket to do it. But same thing with electrons. The outermost ones are the ones that are most easily stripped. And when you strip them, you can form ions. And one of the easiest set of metals is those in the leftmost column, the alkali metals. Well, they're fairly easy to oxidize. Now, we know that the energy levels are quantized, and that's revealed in the atomic spectra. We've talked about that. Countable wave states that are allowed by Planck's constant H in the Coulomb interaction. And what nature tends to do is to prefer that each atomic orbital level is full. So the noble gases have that property of not combining with other atoms because their outer orbitals are full. And that is what nature likes. Nature considers that a stable state. Now, other elements that aren't noble gases in the rightmost column, so for instance, lithium and magnesium and so forth, they'll combine with other elements in order to either lose or gain some electrons and attain an outer shell that is full. So now, when they gain or lose some electrons, they become an ion. They become electrically charged. That's not a problem. But it is the way that nature mediates chemical reactions. In other words, if you're not a noble gas, you're not going to form a chemical compound. If you're out there to the left of the noble gases, like calcium or lithium or something like that, oxygen, yeah, you can make a chemical compound, and you do that by either gaining or losing electrons in the reaction, and thereby forming outer energy levels that are full. And I'm going to go through a couple examples with you. Sodium and lithium. Sodium loses an electron fairly easily, lithium too. And when sodium loses its outer electron, it's just got one, it has an outer energy level like neon. In lithium, it's the third element on the periodic table. When it loses its outer electron, it becomes, its outer energy level is a lot like helium. All right, so let's take a look at lithium first, see how that works out. Lithium 7 is the most common form of lithium. And that means that in the nucleus there are 3 protons and 4 neutrons. Right now, its ground state, or its N=1 state, is full. There's 2 electrons down there when it's a neutral lithium atom. A neutral lithium atom also has one more electron. That's in the N=2 level, and that's where the excitement begins. So let's take a look at this. Okay, here's N=1. Okay, and let's put an electron, 2 electrons there. One of them is up and one of them is down. And the second energy level, I'll display it here like this, a little higher orbit, higher energy, N=2. And there's only one of them out there. So that's the one that's going to get burglarized. It's the one that's going to be stolen by some other atom. Because that's what atoms do. Some of the atoms, what we're going to find is that some of the atoms, if they can get one electron, if they can get this one off lithium and fill their outer energy shell, they'll be happy as a clam. They'll be happy to do that. So let's look at lithium. Okay, you want to either strip that single outer electron, and therefore you're down to a filled N=1 orbital, or you want to get another 7 electrons and fill the N=2 orbital. All right, so what nature tends to do is to strip that single outer electron instead of adding 7. It's easier to strip 1 than it is to add 7. All right. So the natural stability mode for lithium is basically to ionize it once. You strip that outer electron, fairly easy to do, and it becomes a lithium plus ion. And then it will combine and be attracted to a negative ion. Right? And when you take away that outer electron of lithium, Now you're down to the outer orbital that looks like neutral helium. Let's take a look at sodium. All right, now here's a comparison of the sodium atom that's neutral. It has 11 protons, 12 neutrons in the nucleus, and then it has 11 electrons, 2 in the first energy level, 8 in the second energy level, so the second energy level is full. And then the third energy level, it just has one pokey electron out, way out there, easy to steal, right? So let's steal it. Let's ionize that neutral atom, and when you do, you have a sodium ion, positive sodium ion. It's only got 10 electrons, but it's 11 protons, so the net is plus 1. It's a positive ion. And now let's compare that sodium plus ion to a neutral neon atom. Now, neon is 10 and 10. 10 protons, 10 neutrons. And neutral neon is 10 electrons, right? And so when you ionize sodium once, that outer energy level looks like neon's outer energy level. But you're an ion, you do have a net charge. Okay, so you can be attracted to a negative ion or a negative charge. And that is what happens with table salt, sodium, the salt of the earth, NaCl. And that's the electromagnetic interaction between two ions, the positive sodium ion and the chlorine ion. Matter of fact, that's how salt is formed. The chlorine burglarizes the sodium, so it grabs that outer electron, it becomes negative, and its outer energy level is full. Sodium loses an electron, its outer energy level is full. So both of those ions are happy as a clam, and they bind together. And you get this cubic structure of table salt. It's kind of cool. Now, a little bit of terminology. The word valence, valence electrons, that's the terminology for the outer electrons. Okay, so all the chemical properties and stuff that Lavoisier and all those guys found over the centuries, we now believe the theory is that it's all because of what valence electrons are doing. They're being burglarized, or they're bonding together. They're forming some kind of an ion. They're going missing, or they're being added to another atom. All that stuff. The valence electron, it's the valence electrons that do that for almost all chemical reactions. Right? So the properties and so forth of the chemical elements rise from that outer set. No matter, however many you have, it's the valence electrons that do it. Now, in the second and third rows of the periodic table, the column number tells you the number of valence electrons. Okay, so for oxygen, it's over there in group 6. And so that means that oxygen has 6 valence electrons. Now, when you get down to the 4th row, it's a little trickier. But for the first 3 rows, it's fairly simple. Hydrogen has 1, and helium has 2 valence electrons, and that's it. I mean, it's full. And then rows 2 and 3 follow this same principle. And if you're thinking to yourself, Dr. B, come on, rows 2 and 3, that's not really that much. It's a big periodic table. Well, it is a big periodic table, but did you know that 90% of the atoms in Earth's crust, they're from the second and third row. 90% of the atoms in Earth's crust are oxygens, silicons, Si, and aluminum atoms. Pretty cool. All right, so we're not just, whistling Dixie here. This is a fairly important set of rows in the periodic table. Right? And let's go back and talk about NaCl, sodium chloride, salt. And just to remind you, the elements on the right side of the periodic table tend to be stealers of electrons. So I put a little image over here of a burglar, right? And that's because chlorine, for instance, in the red box on the right, if it can add one electron to its outer shell, then it will have the same outer shell as argon, which is one block to the right. So chlorine prefers to do that than lose 7. Right now, sodium, we already talked about, that prefers to give up one. So that's the one that gets caught napping. So I put a little napping icon over here by sodium. And these elements over in the first two columns, yeah, they're fairly easy to catch napping. And the fluorine and chlorine over here, oxygen, they are better at stealing electrons from those guys all the way over on the left. All right? So that's a general pattern, and but notice that I haven't really talked too much about the stuff in the middle. The stuff in the middle, those atoms in there, they're not really strong enough to criminalize the atoms to their left, all right? But they still form molecules, and those molecules are formed not by stealing electrons, forming a positive and a negative ion, but by sharing electrons. And that is a quantum mechanical effect that we call covalent bonding. And that's the topic for the next lecture.